I don't know, Juan, would you like to?
No, only to say, okay, good afternoon, everybody. And as Juan commented before, today's talk of Lorenzo Pareschi concludes the BIOMAT 2021 cycle of conferences that this year, due to the restriction of the pandemic, has been developed online. I want to thank Lorenzo and with Lorenzo to all the participants for the generosity with which they have contributed to the success of this edition. Hopefully next year we can face it from other perspectives and we can take up the idea to face-to-face meeting. Then we hope to see you all in Granada soon. Then Juan, if you like to introduce Lorenzo or David, I don't know.
Okay, so I will present our speaker today, Lorenzo Pareschi, and let me tell you that he got his PhD in mathematics from the University of Bologna, and then he moved to the University of Ferrara, and as of 2007, he's a full professor there in numerical analysis. He has held various visiting positions as well, including one at the Imperial College as an elder fellow and another one at the Technical University of Munich as a John von Neumann professor. Concerning his research, a great deal of his research topics actually revolve around the hyperbolic equations and kinetic models, more precisely on the numerical simulations and also on the wide modeling applications in various different contexts. Here we quote an influential monograph that he co-authored with Giuseppe Toscani entitled Interacting Multi-Agent Systems, Kinetic Equations and Monte Carlo Methods. And let me also quote a highly cited paper together with Giovanni Russo on IMEX Runge-Kutta schemes and their applications to hyperbolic systems with relaxation. More recently, Lorenzo has focused on additional research lines, including, for instance, uncertainty quantification, machine learning, and optimal control, and perhaps some of those will relate with what he's going to tell us about today. So, Lorenzo, whenever you are ready, please.
Okay, so thanks Juan and David for the kind introduction and the invitation. Of course, I mean, the last time I was in Granada, I was enjoying a nice lunch together with Juan Soler. So I feel rather nostalgic of those days, but let's hope that that in the future we will have the opportunity to meet in person. So I took advantage of this invitation of this slot within the BIOMAT 2021 series of seminars to present some recent research that I recently have done together with several collaborators that I will mention along my presentation. Essentially on the spatial spread of epidemics, so the introduction of a spatial dependence in models that consider epidemic dynamics, and in particular in presence of uncertain data. So this is an outline of what I plan to present. Probably this is a little bit ambitious, so I will have to skip some part, or eventually to run a little bit on some details. So basically, my talk is arranged in two main parts. In the first part, where I deal with essentially hyperbolic compartmental models, and I will show how to essentially to build up this kind of models, and in particular how to extend this kind of model to the case where you have a network of interacting cities or regions or villages. And I will essentially use this modeling to consider an application to the emergence of COVID-19 in Italy, in particular in the region Lombardy. And in the second part, I will consider a fully multidimensional case where the modeling is a little bit more complicated in terms of PDEs. Since I will consider kinetic transport equation, I will follow essentially a similar path as in the first part of my talk, and I will consider the one particular application where we consider a realistic model which can be applied also to some geographical context like region. And I'm going to focus in this case on the Emilia-Romagna region, which is the region where actually my university is, so in the city of Ferrara is. Of course, we have all seen that the COVID-19 pandemic has led to a strong interest from researchers to design new epidemiological models, which are essentially capable to describe the process of the epidemic. And these models have been updated day by day according to the new discoveries that were essentially made considering the peculiar characteristic of the COVID-19. In any case, most classical models are based on the idea of compartments, and they represent essentially the spread of the epidemic only concerning the temporal evolution of the disease by doing some homogenization, some average process. And usually they ignore spatial effect, and if these spatial effects are considered, somehow these are considered by coupling system of ordinary differential equations. So the way we think at spatial effect is quite different. We of course, I'm working on partial differential equation, so I try to put my experience in this field, and we considered both the case of networks, but networks where the interaction occurs through partial differential equation, through one-dimensional partial differential equation, as well as to more general, fully two-dimensional space dynamics. In addition to this modeling concerning space, one very important aspect is the introduction of a certain degree of uncertainty, actually a very large degree of uncertainty, if we think that all data that we had concerning the pandemic, especially at the very beginning of the pandemic, were affected by a large level of uncertainty. And so any model which is data-driven, or where you want, in any case, to try to reproduce scenarios which are somehow related to data, need to take into account certainly this aspect. So I will, of course, I don't have the time to make an introduction to compartmental models in epidemiology. On the other hand, in this same series of seminars, there have been the nice talk by Henri Beresticchi. So I will refer to his talk for those that are interested, in particular, to a nice introduction on this kind of model, and especially in the particular case where you consider the space dependence extension in the direction of reaction diffusion equation. Let me just remind that the basic model is the SEIAR model, where essentially individuals are separated in three classes: susceptible, infectious, and recovered. And there is a transition between the three classes, which is governed by certain parameters. Essentially, the susceptible are individuals which have never been in touch with the virus. The infectious are those which have been infected and can transmit the disease, whereas the recovered are those which are healed or deceased. And so in any case, in the case they are healed, in the SEIAR model, you assume that they acquire permanent immunity. In the model, you have essentially 3 ordinary differential equations, and essentially the infection is proportional to the product of the susceptible and the infectives, and the rate beta governs this transmission of the infection, whereas the parameter gamma is the inversely proportional, essentially, to the amount of time that the individual spend as in the infectious compartment, and it's the recovery rate. You have a classical picture on the left of a simulation of the SEIAR model in the case where the ratio between beta and gamma, which is the basic reproduction number, is above 1. So you put a small seed of infected in the population, and you see that this is the red curve, and you see that the infection grows, it reaches a peak, and then because of the acquired immunity of the large fraction of the population, you see the peak is essentially when 0.4 of the population has been essentially belongs to the recovered compartment, and then it starts to decay, and essentially and eventually will disappear. It's a deterministic model, of course, and it doesn't contain any spatial information on the epidemic spread. It has been introduced by Kerman and McKendrick, essentially at the beginning, in the late 20s, in a series of papers. And I refer here to the survey by Efcott on various on the derivation of the model and all possible various extensions. So let's consider immediately the issue of uncertainty. So uncertainty in the data, in my viewpoint, is considered in the following form. So basically, you assume that you have some statistics about uncertain inputs. So there's some statistics that you acquire in some sense concerning, for example, the initial number of infected, or the transition rates that you have between the various compartments. And once you have these informations, you essentially you feed your SEIAR model with this information, and you will get solution either analytically or numerically, which will depend, of course, on this parameter. Basically, changing these values will affect the change in the solution, and then, of course, you will have essentially a bunch of solution out of which you want to get some information, for example, some statistics about the desired outputs, like the expectation of the number of infected, or the variance of this number. Of course, so I will give you a very simple example here, since the model is very simple, and so some computation can be carried out even by hand. Consider the SEIAR model, and let's imagine that you have an initial number of infectious, which is given by a lower bound, a lower deterministic bound. This is actually the case that you have typically. The number of detected infected is represent always a lower bound of the real number of infected. So you can certainly assume that the real number, so from a statistical viewpoint, is larger, and you measure this by some constant mu and some random variable z, which has some given distribution. For example, it may be a uniform, or it may even be estimated somehow by some process. Nevertheless, if you assume to have the distribution to assign the distribution of your random variable, then you can compute, as in the deterministic case, the initial exponential phase of the disease, which is which essentially it has the same structure like the deterministic case, except for the amplitude factor at the beginning, which is the initial data plus the uncertain perturbation. And so out of this solution, you want to compute some statistical information. For example, if you compute the expectation, so you revert back to some deterministic result by computing the expectation, it is easy here to see that the expected solution is exactly the same as the deterministic solution that you would have obtained by considering initially the average number essentially of infected in your domain. Of course, this process typically is not carried on analytically, but you have to carry on in more complicated model this process numerically, which means that basically you need to have two main tools. One is, of course, a numerical method that solves your model, but this is quite obvious. But on the other hand, you need to have an efficient way to accumulate statistics. Okay, so for example, you can imagine that you have many values of the variable z, which is sampled through some Monte Carlo method from the probability distribution P. But this means that in order to have reliable statistics about your outputs, you need a very large number of realization, because everybody knows there's low convergence of the Monte Carlo method. But since for every realization, the price you have to pay is the solution of the PDE, this becomes extremely expensive from a computational viewpoint, especially if you think about PDEs, networks, or multidimensional simulation. So the approach we will follow here, which I will barely touch here in my talk, is to assume that the probability distribution function is given, and to adopt a stochastic formulation which is based on orthogonal polynomials with respect to the probability distribution, in such a way that if the solution is smooth in the random space, you have exponential convergence of the whole procedure, which from a practical viewpoint, it means that with very few statistical samples, you get an accurate estimate of the quantity of interest at the end of your simulation. Okay, so then the compartmentalization game. Of course, you can extend this idea of compartments as you want. So you just add the one compartments accordingly to the characteristic of the infectious disease, of what you think is important. For example, in the case of COVID-19, as soon as we were getting more information about the disease, about the role of pre-symptomatic, of exposed and asymptomatics, it gives the motivation to build up more structured model. And here you see two examples. On the left, the model by Gatto and co-workers, and on the right, the model by Giordano and co-workers, where you see that you have many compartments accordingly to the information that you want to put into your model. Let me say that one of the problems in general, however, is that matching these models with available data, it's in general a real challenge. Even if the model is data-driven, it's still a challenge. And the main reason is that essentially all the solution of this system of ordinary differential equations are exponential. So which means that they are highly sensitive to the parameters. So for this reason, one general rule of thumb which has been adopted by the largest majority of the authors is to fix all the parameters which have some clinical relevance and to embed into the modeling essentially some information that comes from that side, which you don't try to fit with the data. For example, the incubation period is something that you can imagine for a disease that you know it from clinical data. So you avoid to put this aspect into essentially the fitting process, the matching with data, in such a way that you have a lower number of parameters to identify, and then you have a more stable process. Okay, so adding spatial dependence, it's done classically by adding diffusion. This is the parabolic SIR model, where you, on the right-hand side, you simply add a diffusion, three diffusion terms, where this is typically a self-diffusion process in the model that I've considered here. There are also cross-diffusion models. So the diffusion coefficient, of course, may also depend on space. There are two major line of research that you can see in a model of this type. In some cases, the diffusion process is really associated with the population dynamic, which means that these operators here on the right really describe the fact that susceptibles are moving, the infectives are moving, and that the recovered are moving, okay? And then typically in this kind of model, let me refer to this as population dynamic, which is the kind of model I will also work on. The diffusion coefficient of susceptibles is larger than the diffusion coefficient of infected. This is true both in animal population, because I mean the troubles which are caused by the infection, but as well as in a human population because of the restriction of the quarantine and so on. On the other hand, there's another direction which has been also presented very nicely by Pareschi, is the case where you don't consider any diffusion in the susceptibles, but you consider just the diffusion in the infected. So basically, what it means is that the diffusion process is no more related really to the population movement, but it's more related to the movement of the infection itself. So the people acts more as a background, and then you see the infection, how it propagates on this background. In any case, the parabolic character of this model may lead to the disease to propagate instantaneously over large distances. So for this reason, what we have considered is the introduction of hyperbolic models. And I show you first the hyperbolic SIR model. This model, we introduced it in a joint work with Giulia Bertaglia. So in this model, each class of individual is essentially separated in two groups. This is one-dimensional, and consider the one-dimensional case here. One group of individuals which are moving towards the left with a given speed, and we denote this in general those group with the sign minus, and a group of individuals moving towards right that we denote it with the plus sign. And this is the same for all individuals in all classes. So then we have a set of transport equations on the left, where lambda s, lambda I, and lambda r are the characteristic speed of the three classes. We have some incidence function which characterize the transmission of the disease. I just generalize it here, but in particular, this in the case p equal 1 and k equal 0, it is exactly the classical nonlinear transmission rate that we have seen right now. This general incidence function takes into account the possibility to have nonlinear interaction. We will not actually use it, so in the sequel we will just consider p equal 1. But one important aspect is that it allows you to take into account the natural social distancing process which takes place in many epidemiological phenomena, not necessarily by restriction which are imposed by some policymakers, some government, but natural restriction which are just caused by the fact that people are aware of the disease, so they are more worried, so they take more precautions. So as you see, the numerator here, it has a factor k which multiplies the number of infected. So as the number of infected grows, as naturally the population have the tendency to be more cautious. The last term is a relaxation term, which basically provide an homogenization of the process, because as the relaxation time, tau s, tau I, and tau r becomes smaller, as the two populations that moves toward left and toward right takes essentially the same value, so they are homogenized. This relaxation process, in fact, as we will see, it's essential, this relaxation time, in recovering the corresponding diffusion model. This can be done as follows. So first, let me note that this is a set of 6 equations, of course, because you have to consider the population that moves right and the one that moves left. So we can write it in equivalent macroscopic form just by introducing the corresponding fluxes, J, S, Ji, and Jr. And so you have a set of three equations for the corresponding density S, I, and R, which are the sum of the density that moves left and right. And then you have a set of 3 equations for the corresponding fluxes. Now, if you consider the following asymptotic limit, where you introduce this diffusion coefficient and you keep this diffusion coefficient finite while you let the relaxation time go to zero, then you can see immediately from the last 3 equations that you multiply everything by tau, and you send it to 0, and you get exactly that for example, for the equation for the susceptibles, the J is equal to minus ds, the derivative of the density of S with respect to X, which is exactly the equation here, which are the so-called fixed laws for the various density. And of course, if you insert these 3 equations now into the first group of equations, you exactly get your second order parabolic model that we have seen before. So let me point out that in the case you consider equal propagation speeds and relaxation time, then the total density in our kinetic model, they satisfy exactly the Goldstein-Taylor model. So, which means that you, in this case, in this particular simplified setting, you can apply all the result, even in the case you consider nonlinear relaxation time by Lyons and Toscani, by Goltz and Salvarani. But in the case where the propagation speeds are different and the relaxation times are different, then the situation is different, is more difficult. And I mean, we are still working on this, but it's an open problem to establish the rigorous diffusion limit for this kind of model. So concerning the reproduction rate, this is quite difficult in general to estimate a number for reaction diffusion equation, which is time independent. There are several works on this. I mentioned here the work by Magal, Webb, and Wu of 19, which also makes some nice survey of different approaches that can be used. In our case, we limit ourselves to consider we are more interested in the time-dependent reproduction number. So if you assume no inflow-outflow boundary condition, and we just integrate the equation for the infectious population, then you get that the total number of infective, the derivative is larger than 0, so we have a growth of the total number of infected if this number, R of t, is larger or equal than 1. So we define, therefore, the time-dependent reproduction number exactly in this form, which is the integral, essentially, of the incidence rate function over essentially the fraction of infected which moves toward the recovered compartment. So it's of course, if you remove the dependence from X here, this definition will coincide exactly with the definition of reproduction rate for the corresponding SEIAR model. So this is a very simple numerical example for which shows the difference between the possible behavior that the model can describe and the difference between the hyperbolic and the parabolic regime. So this is an heterogeneous environment in the domain 0, 20 in X. It's just a sinusoidal variation of the contact rate. The overall reproductive ratio is above 1, so we have that grow in the epidemic, starting from a seed, from a small number of infected at position 10 initially. And you see on the left, I mean, on the x-axis, you have the time, the integration time is 0, 10. And you see on the left, the hyperbolic evolution, which shows that the pandemic spreads, but it remains confined within the computational domain in time. Whereas you see on the right, the parabolic regime, which shows that the pandemic grows and continue to grow all over the computational domain. So now let's try to do something to use this approach, this modeling, to design a realistic model for the diffusion of an epidemic like the COVID-19 epidemic on a network of cities. So what we have considered is a multi-group hyperbolic model, which includes, together with the classical SEIAR compartment, also the compartment E of the exposed. So basically those individuals that they are latently infected, so they have been infected, but they cannot transmit the disease. And most important, the compartment A, which is the compartment of asymptomatic population, which, as we know, it plays a determinant role in the propagation of COVID-19. So beside these, because this compartmentalization of it's rather pretty well known and has been used by other authors like Gatto, for example. Here, one of the major novelty consists in considering each compartment subdivided in two groups of individuals. So we subdivide it into commuters, which travel which moves along the space domain or along the network with a certain speed, and a stationary population of non-commuters. Why this is an essential feature? This is an essential feature, especially when you want to apply this kind of modeling to a population of human being, because this will prevent the unrealistic effect of mass migration in which the entire population moves through the network. You have that only a fraction of the population really commutes from one city to the other. You can even identify these and you can estimate this from data. The majority of the population stays in the urban area, work in the urban area, and has a different kind of process. It's a small scale process compared to the long scale process of the motion of commuters. So this has been essentially introduced in a joint work with Giulia, and it takes its roots in a joint work with Boscheri, Di Marco, and Pareschi that I will present later on. So the commuter dynamics here, it has a similar structure to the dynamic that we have seen in the SEIAR case, except that we have two additional compartments, as we say, the compartment E and the compartment A, and two additional, so one additional incidence rate function, because we need to distinguish in terms of transmission of the disease between essentially the probability of enter in contact with an infected population with an infected individual with symptoms, so with heavy symptoms, and an asymptomatic individual. So we know that typically the majority, let's say, of infected individuals with symptoms have been detected, and so they have been quarantined, whereas all the asymptomatic individuals, they have been completely free to move, to travel, and of course to spread the disease. For this reason, we typically assume that these incidence function here, the first one, Fi, will give a very small contribution in the dynamic, because especially when you talk about traveling along the network, because you assume that these individuals are essentially identified the majority, and so they cannot travel. Then you have the other thing is that, of course, A is inversely proportional to the incubation period, and then you have a probability sigma, which is the probability of an exposed to develop symptoms or not. All these essentially are somehow, let's call it, clinical information that we can include in the model by taking them outside from the fitting process. So what is where the interaction between commuters and non-commuters took place? Well, this took place in this incidence function, where you see that the interaction is with the total number of infectious and the total number of infectious asymptomatic, and these are computed by summing up the density of commuters and the density I0 and A0 of non-commuters. The non-commuters, on the other hand, they satisfy in the nodes of the network, essentially, or in certain region if you don't have a network, but just a simple one-dimensional domain, in this case, just a set of ordinary differential equation characterized by the same compartmental model. All this is considered in presence of uncertainty, which means that all our variable depends on space, time, and eventually a set of random inputs, which will take into account the fact that the data that you have are affected by uncertainty. I will not spend time on the diffusion limit, in the sense that the process formally is the same as we have seen before. So you just fix introduce the diffusion coefficient, and you let the relaxation time to 0 by keeping the diffusion coefficients finite, and then you recover the corresponding diffusion model for this 5 compartmental structured system. The reproduction rate is slightly more complicated to be evaluated in this case, because you have more compartment which can spread the disease. You don't have one single compartment. And so the approach that we follow is the approach which is referred to as the next generation matrix, which is used in ordinary differential equation. And we adapt the same process to the average quantity over our domain omega. So what you can see is that you get this expression for the reproductive rate, which is the sum of 2 contributions. And you can clearly identify a first contribution where essentially it's the quantity that appears are the symptomatic infectious, and the second contribution, which is due to the asymptomatic part of the population. So that's basically the simplest scenario that you can imagine to understand this sum of two contributions. So how do you extend this approach to network? I've already presented the model a little bit by talking about network, but up to now, in fact, there is no network in the structure. But the idea is the following: you build up your network. In the nodes, you have that the presence of the non-commuters, which evolves accordingly to ordinary differential equations. So you have a network where the nodes evolve, which is whereas in typical network the nodes are non-evolving quantities, for example, in traffic flows and so on. In this case, the networks evolve in an autonomous way, and whereas on the arc you solve the hyperbolic PDEs. Of course, you need to in order to ensure the correct coupling between nodes and arc, you need to specify specific transmission condition and nodes, and this can be done essentially following the general theory of hyperbolic transport network, like for traffic flow, and I refer you to the book by Piccoli and Garavello. I will not enter further into the details. So now that we have a model, let's try to apply it to the emergence of COVID-19 in Italy, and to see how we can try to simulate the various scenarios. First, what we need to do is to set up a network. In our case, we consider a network composed by the 5 cities which has been mostly affected initially by the pandemic. So the city of Lodi, Milan, Bergamo, Brescia, and Cremona. Lodi, in particular, the small village, I mean the small city, let's say, of Codogno. It has been the origin, it's assumed to be the origin of the pandemic in Italy. We have considered the 5 arcs, which essentially takes into account all possible connection between the different cities, and they essentially cover the majority of the possible path of commuters. So let me stress that. For example, if you move from Brescia to Lodi, for example, typically what you do is that you move through the city of Cremona, but in the model you're not you can estimate actually precisely from the transport matrices the amount of people that really goes and stop to Cremona and those that just pass to Cremona without having any interaction. And that's exactly what the model does. So there are also direct connection essentially from Brescia to Lodi, which goes all the way here to Cremona, but there is no interaction within the node. And this is all estimated by a mechanical essentially setting, which is based just on the distances between the different cities, on the percentage of people that move from one city to another, and the characteristic speed. So you basically set up the characteristic speed in order to respect the fact that you have these percentages of movement in each day. You can do this really like a periodic motion, so just by fitting it in such a way that you open and close the exit of the population by producing really oscillations along the network. But we have seen that in terms of epidemiological result, this doesn't change the result. It just produces wiggles on the solution. So we decided not to adopt this specific setting. So we just distributed the population movement uniformly along the daytime. Numerically, we adopt a second order implicit-explicit Runge-Kutta finite volume collocation method. The advantage of this method, let's say, are essentially twofold. On the one hand, thanks to the collocation method, we have a non-intrusive approach, which for smooth solution permits to avoid a high computational cost, because with very few collocation points, we can get very good statistical information. And being non-intrusive, we can use the standard deterministic computational code. On the other hand, the method, thanks to the use of the implicit-explicit Runge-Kutta approach, is able to preserve accuracy also in the diffusive limits. So basically what is usually referred to as asymptotic preservation, which is very well known, especially in the study of diffusion limit in other fields. So basically we adopted 2 well-known approaches which has been used even in some joint work with other authors to study the diffusion limit. The model calibration, just a few words, because this is a very delicate aspect. What we have done, we have used the uncertainty essentially to take into account the potential calibration error in the model. So what we have done is essentially an estimate from below of the calibration of the parameter in as follows. So we have used an homogeneous ordinary differential model for the whole Lombardy region in order to calibrate essentially all the parameter, and we solved an optimization process using the reported cumulative number of infected in our fitting. Of course, this makes sense. Why? Because at the very beginning of the pandemic, we have very small numbers, and it doesn't make much sense to try to go and to try to estimate locally really what are the specific parameters, because if you have 15 infected, 20 infected, this is completely, I mean, it's completely unreliable. by considering all the number of infected over the region, we may assume that probably the process is more reliable, and even if averaged, it will give us some more realistic information. Of course, since the reported cumulative number of infected represents a lower bound of the real number of infected, we then introduce through the uncertainty the possibility that this number is in fact larger. An interesting aspect is that even if we focus on the period February 27 to the end of March, and basically we perform this calibration between February 27 and March 9, because at March 9 there had been the initial day of the Northern Italy lockdown, and so everything has changed. The calibration is performed backward in time. It means that basically we put in the optimization process even the initial time of the pandemic, and we start with one single exposed individual and 0 in all other compartments. So basically you have some epidemic parameter, you start with one single exposed individual, and then you compute what is the amount of time you have to wait in order to get the certain number of infected which has been observed on February 27. Why this is interesting? This is interesting because it gives you the one main unknown that you have from the data, which is the number of exposed and asymptomatic. These are how you initialize your model with exposed and asymptomatic. So the idea is to solve the backward problem in order to get an estimate of the exposed and the asymptomatic at the date February 27. Just for curiosity, if you do this, you get an initial estimate of the pandemic, which is on January 14 in the region. Okay, so once you have done this calibration, of course, the subsequent social restriction, you implement it by essentially modifying the incidence rate just by recalibrating the model essentially at the lockdown. Actually, we have observed that it's important to recalibrate the model after March 9 because it has been a strong lockdown. There has been a second lockdown later on, which can be taken into account even without the need really to recalibrate the model because the data are less sensitive to the changes. And then the uncertainty is included, as we said, in the initial number of infected as the beginning. And we basically, our assumption is that the initial number of detected infected with symptoms, not asymptomatic, with symptoms, were essentially about 1/2, not more than a half the real number of infected with symptoms. And this has, of course, an influence on also the compartment E, A, and of course S, because for every realization of, so whenever we change the initial value of the data concerning the number of infected, then of course the number of exposed and asymptomatics also will change because you have to perform the calibration back to get these values. Even the transmission rate between the infected is affected by uncertainty for the simple reason that the I0 is the number of detected infected, so these are quarantined, but the other that we assume that these are not, that have not been detected, they act as asymptomatics in the dynamic, even if they are not asymptomatics or very close as asymptomatic, so they can spread the disease actually. So which means that the rate that we apply, the transmission rate which is due to people having symptoms, has to take into account the uncertainty, because you need to model the fact that the fraction that you had here will behave more or less as the asymptomatic population. So this is the epidemic spread over the network, and we can show a simple movie when in the pink circle you see the total number of infectious people, so even the asymptomatics, and on the connection the width of the connection is proportional to the number of asymptomatic people that's traveling among the various cities. So you see basically that it starts from Lodi, as I said, and you see that initially Bergamo has a much larger number of infected compared to the city of Milano, for example, but all of a sudden then also the city of Milano started, which has a much larger population. And then at the end of March, the total number of infected in the city of Milano was in fact larger than the rest of the network, but you can really see how heavy this has impacted on the city of Bergamo and Brescia compared to the number of individuals. These are plots of essentially these are the plots that we have concerning the reported the cumulative amount of infections in the black circles, and you see basically how the 95% confidence band in our simulation lies exactly on the data as we were expecting, essentially, and the line that you have in the middle is the expected number, but these are those with symptoms. Whereas here you see that the number of asymptomatics is actually much larger compared to those with symptoms, which are essentially the red bands. So basically it's between 9 and 10 times actually in agreement with actually what was estimated by other sources. And you also see how the lockdown affect immediately first the exposed compartments, and then they affect the compartment of asymptomatics and infected without producing these, I would say, these small discontinuities, not discontinuities, I mean loss of regularities that you have due to the change, the rapid change in the parameters. What we have done, in fact, we have done a calibration exactly in correspondence of the vertical dashed line without trying to smooth it. Okay, so you see basically the results are pretty good. It shows that the model is able to describe this kind of situation and to take into account the effect of the transportation between the different cities. So in the last part, I will quickly survey the multidimensional case. So how can we deal with a multidimensional setting? So in the multidimensional setting, our modeling is more kinetic based in the sense that we are in a two-dimensional scenario, and so of course individuals don't have any more just two directions, but we have all possible direction. So we assume that individuals can move with a certain velocity v, which belongs to the unitary circle, and we denote with fs and phi and fr the respective density. So we have a transport process on the left and the relaxation process together with the reaction term on the right, which is analogous to the previous one, except that the transport is multidimensional, and then the relaxation is towards the specific density of individuals in that particular position, which is computed by integration over the velocity field, like you do in classical kinetic theory. If we now try to see what happens in the diffusion limit, now you introduce the flux function as before. You have the three equations for the density, you have the three equations for the fluxes, but of course these are vector equation, but these equations are not closed. These six equations for the fluxes are not closed because they involve higher order moments of the kinetic densities, as you can see from this flux term, as it happens usually in kinetic theory. Nevertheless, you can use this moment equation to compute the diffusion limit, because you can again introduce the diffusion coefficient, and you can again keep the quantity fixed while letting the relaxation times to 0. Then following, let's say, I would say the classical methodology that you have in diffusive limit of transport equation, by using the kinetic equation, you observe that the kinetic density lose their dependence from the velocity, and they are projected towards their averaged quantity as I and R. And from the flux function, you recover the fixed law. You plug these 3 into the first set of the equation, you recover the multidimensional parabolic SIR model. So we can perform a similar test as the one we have performed in 1 dimension. Here, let me stress that computationally, we use a polygonal control volume. So we use an unstructured discretization in space because we want to deal with realistic geographical setting. And we use the same IMEX method that we have used before in order to get an asymptotic preserving scheme in the limit. So the initial condition is similar to the one that we had before, with an oscillating heterogeneous transmission rate on a square in this case, and a reproduction rate which is above 1. Now the seed is at the center of the square, and you see on the top the hyperbolic dynamic, and on the bottom the parabolic dynamic, described by the same model, same numerical scheme, and you exactly observe how the hyperbolicity limit the spread within a certain region, and also permits to keep these small outbreaks that you can observe, these spots of the epidemic, whereas in the diffusive regime, all these features are essentially lost, and you have a classical diffusion process which spread the disease all over the computational domain. We can extend this idea actually to be fair in terms of modeling. We have to say that we first designed the commuters and non-commuters dynamic in the case of the kinetic model, and then we think about the model in network. But I follow this presentation because it's easier, of course, the 1D model over network compared to the kinetic structure. So we split it into commuters and non-commuters again. The dynamic of commuters in this case, the only thing is that the computational cost here is pretty high. So, and also the matching of a multidimensional model with data is much more complicated compared to a 1D model. So basically, we use a model where we essentially collect together all the undetected individuals which can potentially transmit the disease, namely the exposed and the asymptomatic. So the compartment E here include both the compartment E and A that we have seen before. The main difference is that the non-commuters satisfy a diffusive process in the urban region here, because this is a two-dimensional domain. So basically, we identify an urban region where the dynamic acts on a small scale, and this is a purely diffusive dynamic. Whereas on the long scale, we consider the hyperbolic nature of the dynamic of the transportation, and then where the commuters enters into the game. Once you have the compartment FE, we can recover the asymptomatic, just assuming that you have a constant fraction Xi of this compartment, which gives you the latently infected, and 1 minus Xi, it gives you the asymptomatic individuals. Let me also say that this was introduced in this idea of combining the two was introduced in a paper by Vigery and co-workers, where they were solving reaction diffusion equation. The reproduction number is computed again by essentially the next generation matrix, and it gives us again a sum of two contributions analogous to the one that we have seen before, where one is given essentially by this F tilde E, which is the component, as you see here from the definition, is the 1 minus C. So this is due to the asymptomatics. part of the population, and this one is due to the symptomatic part of the population. In this case, we have considered a different scenario. This has been the first geographical scenario that we have dealt with, which is the region of Emilia-Romagna. Actually, this is Ferrara, so where I am right now. And the reason is that this is just south from the Lombardy. Lombardy is here in the north, and in this border, especially this border was highly affected by the initial spread of the disease in Lodi. And as you see, a peculiar feature of this region is that these cities are all aligned, and all the connections actually are along this line. And in fact, you can really see that the disease has been essentially has moved along this line by spreading in this direction. And fortunately, I have to say that Ferrara, as you see, is an outlier with respect to this group of points. And this is one of the reasons why the epidemic has impacted in a weaker way in the city of Ferrara compared to the other city of the region. So again, we can build up from the transport matrix the connection. Here, the main difference is that we consider an initial distribution of generic population, which is assigned as a Gaussian, so it's centered in the urban area, and then it decays as soon as you move outside from the urban area. The radius of the Gaussian is essentially proportional to the amount of individuals in the city. The traveling speed has been estimated again from the distances that you have in the network, and the number of people that's moving from one place to the other. And the calibration has been performed again by using the simple ordinary differential equation model of the whole region. You see, this is the time evolution of infected plus recover on the left, which is what we use to calibrate to fit the model. So it is perfectly expected that we have such a very good fit, but it's I mean, it's expected, but not so easy to get, because you calibrate it on the homogeneous setting, but then these are the data of the whole dynamic. So, and these are the data in the three main nodes, namely Piacenza, four main nodes, Piacenza, Rimini, Parma, and Bologna. The continuous line is the computed solution by the model, and the symbols are the data. As you see, there's a pretty good agreement. Of course, you can calibrate all this much better, but it's very interesting that the main characteristics are very well described by the tendency is very well captured by the models. Here you have 2D plots, which basically shows how from the left, from the city of Piacenza, this is the sum of the people that can travel, namely asymptomatic and exposed, and now they have spread from left to right along the main line, and they have diffused the whole essentially pandemic along the region. This last picture, and then I'm done. It shows something which is, even if the two pictures looks the same, it shows something which is pretty important to emphasize, namely the following. On the left, you see the total number of the population at time 0. On the right, you see the total number of the population at the end of the simulation at time 10. The two pictures looks the same, but this is what we exactly want, because basically the model day by day describes the motion of a small fraction of individuals from one city to another as commuters, and then they, at the end of the day, they are back into their cities. And so we want that periodically, day by day, the situation to be exactly the same, since we have no of course demographic variation of the population. So this is exactly the main feature of the presence of commuters and non-commuters. If you solve just with this initial data you can have on the left, whatever equation you want, you know perfectly that everything will spread out all over and will never come back. So conclusions, very quickly. Some research direction that we are following right now. So we are doing uncertainty quantification in multidimensional modeling. In fact, I haven't presented any UQ fact concerning multidimensional modeling. We have a joint, we have a work in progress where we do this for the Lombardia region by extending the complexity of the model and by including uncertainty quantification. It would be interesting also to incorporate an age structure in the population. Of course, this will increase additionally the computational complexity of the model, but this is of course relevant if you want to embed into the model, for example, data concerning hospitalization or data that in any case are of interest for the sanitary system. Of course, as I mentioned, rigorous result on diffusion limit. This is also something we are working on, and eventually other. So thanks for the attention. Here are essentially the 4 papers which are at the basis of this presentation, and you see here all the collaborators which essentially have done the majority of the part of this work. So thanks.
Thanks a lot, Lorenzo. This is very interesting talk, again, on a very hot topic. Okay, so now we have some minutes in order to pose some questions. So as I told you before, if you want just to jump in, open your microphone and ask directly, or else write it down in the chat and we will read it out for Lorenzo in case you cannot use your microphone. While you start to pose your questions, I can ask some already. So I assume, Lorenzo, that once you include the age structure in the model, you can easily incorporate, well, easily, or maybe not that easily, but you can incorporate vaccination strategies into the description. Is that so?
Yeah, sure. Sure, absolutely. So basically I would say that the largest part of our effort has been done considering really the spatial spread. So the construction of the model which described correctly the motion of individuals in space. So, but you can clearly adapt the same methodology in a more structured model in terms of compartments, where, for example, you include vaccinated and non-vaccinated individuals. Just the main problem is that, of course, typically, the more you made the model, let's say, realistic in terms of compartments, the more you increase the overall complexity of the model. And so it's of course very interesting, especially if you want to have I would say qualitative pictures or presenting scenarios, but fitting then that kind of model with data may be really hard.
I see. Thank you, Lorenzo. We have a question by Elena Torres. So if you want to formulate it yourself, Elena.
Yes, first of all, thank you very much for the talk. And I would like to ask about a part of the talk where you showed a network with the cities on the nodes of the network. And I think you said that the model was taking into account that you can go from one city to another, passing through one in between and interacting and also not interacting with it. And I didn't understand how you do that. So that would be my question.
Yeah, well, basically in each node you have, of course, it's thanks for the question. First of all, as I said, I didn't give detail on the fact, any detail about the coupling between nodes and arc, where you have these specific transmission conditions. So basically, what happens is that you will have, for example, that along this line, you have that only a fraction of those that travels here are allowed somehow to interact with the node, whereas the other fraction doesn't interact with the node and simply continue along the path. And how you know this fraction? From the Lombardy network, which gives you basically, for example, the amount of people that moves from Brescia to Lodi or from Bergamo to Brescia. You compute all this fraction, and you translate this fraction into coefficient, and then those coefficient on average, of course, takes into account this fact.
Okay, thank you very much. This is clear now.
You're welcome.
Okay, I have another question, Lorenzo. If I understood properly, you are calibrating your model and you're feeding your model with one single source of data, which is the one coming from the Italian government. Is that right?
Yes.
Okay.
Yes, yes. It's basically which are the official data. But in both cases, let me say one important aspect. In both the simulation that I have presented refer to the very beginning of the pandemic, where we have really very few information and affected by a large uncertainty. Of course, if you apply this same kind of approach, for example, instead of trying to estimate the first outbreak, you apply it for the second wave or the third wave, where we are also already detecting asymptomatic individuals. We have a much larger number. Then one can adapt a different calibration where you try to embed into the model all the possible information that you have. The real problem of estimating the initial outbreak is that the number of information you have is very limited and affected really by a large uncertainty.
Mm-hmm. Well, actually, the other scenario is the one that I was more concerned about, so to say. So once the disease advanced, you started to have more sources of data. And somehow, if you want to use them, you have to design some policy to combine this information, and that is, at least for me, that is an important, an interesting point. How to combine that information, or to feed that combined information to the model.
Yeah, this is somehow there are two possible answers. On the one hand, you can, if this information can be aggregated in such a way that you can recast those information into the compartments that are actually that you are using in your modeling, this is one possible approach. The other approach, if you have more information and this information, for example, concern the hospitalizations. For example, at the very beginning, of course, there's no sense to think about hospitalization because we essentially have no data at the very beginning. But later on, you may think that hospitalization are one of the even the deaf people are rather more reliable compared to other source of information. In that case, the other approach is to include more compartments to modify your model in such a way that you have also the hospitalized individual and other individual. But of course, if we think about the role of the transportation, this will not really modify, I would say, the dynamic of commuters. This will modify essentially the dynamic in the nodes. So the local dynamic in the nodes can be made much more rich, of course, because you have more data, more information. But concerning the commuting, you know that basically you have, as usual, you have asymptomatic people that travel and so on.
I see. Thank you again, Lorenzo.
Just a question, Lorenzo. Have you compared your result? The model is different. You mentioned the work of Pareschi. but they do some simulation about this region exactly in the road in the north of Italy. For them, there is a homogeneous diffusion and a diffusion over the lines, over the roads. And then I don't know if they take exactly one of these roads or not in their simulation. How you compare? Because for you, for example, you have transport term plus diffusion in urban diffusion. You call it's a different way to model.
I think it's different. Well, of course, I heard the presentation by Pareschi, but I didn't at the time to enter really in the details of his model. But the feeling I had is that he was not thinking about the motion of individuals, but how the infection spread along the communication lines and along the other region. So one problem that you may have, but is that it may be not so easy to match this with data, because typically you have information about individuals in terms of reported data, and this is one of the reasons why we tried to follow this essentially this approach. So in our case, our model is really a model which is based on a population dynamic. So we basically assume that along the main connection you have a hyperbolic motion, whereas locally in the cities, or if there are nodes like in the network, you just have ODEs. But if they are in a fully two-dimensional case, you have the diffusion processes.
Yeah. Okay, thank you.
Okay, then maybe we can have one last question by Rafael Rodriguez Galvan. Rafael, would you like to formulate it yourself? Else I will read it out. It's a question that we have in the chat. So,
okay. I can.
Yes, please go ahead. Go ahead.
I was wondering if this model is able to be extended to a wide number of cities, including a small village. I was thinking in the population which is not in the big cities, but also in other smaller cities.
Yeah, this is actually, it's a very good question, in the sense that absolutely, I would say in some sense, both models, they have been designed specifically in principle to take into account this. Why? Because actually in the network model, we don't have simply that these two cities, for example, Bergamo and Brescia, that are connected, but we simulate actually the whole process of motion and potential contagious along the line, along all possible paths between Bergamo and Brescia. This is, in our case, is not just simply a transport, but we assume that there are potential sources of contagions also along this motion. Of course, it's very difficult because we barely have data concerning the cities. Okay, so even we typically have a lot of data aggregated for the region. As soon as you move to the cities, the data are reduced. You have less and less data. It's hard to have detailed data. You have to ask to send letters. They are not released in public, many of these data. So you can imagine to try to have real information about villages. That would be great, because in both cases, the network, and even more in the two-dimensional case, where whatever information, geographical information, can be included in the system, then that would improve, of course, the quality of the result. But the real problem is that the available data really up to now are really limited.
Okay. So I think that we can conclude here. So thank you again, Lorenzo, for the talk and for the question round. And let me also thank all the speakers that accepted our invitation to participate in this series of seminars. And of course, let me thank you, all of you who are attending, for being here. And let's hope for the best in the future. Stay healthy, meanwhile.
Okay.
Thank you, Lorenzo.
Thank you so much.
Thanks for the invitation and for the attention.
Corta, Juan, la grabación.
Hablamos así. Un momentito y cierro, se me había olvidado.